Hello, everyone. My name is Rakshit. I work for Intel as a developer evangelist, and I will be conducting today's workshop on GPU optimization. So today's topic is mainly workgroup mapping and GPU occupancy calculator. And in about 4 weeks' time, so we will have the second edition of this one. Mainly, we will look at memory optimization. Right. So with that, so I'll turn off the video for now. And um, okay, so the screen is shared, I'm guessing. Um, so mainly, so I put up a screen here. So we will be doing this workshop on hands-on workshop on Intel Developer Cloud. So if you have already used any of the Intel products and you have a login, so you should be able to directly log in. So for now, you just have to log in. So we will show you the next steps. So for people who don't have a login, so you can click on Get Started on this website and then create an account in the meantime. And then later we will show you the next steps. First, I will go through some slides on introductions and then eventually we will jump into the cloud and then do some hands-on code exercises. So if you have access to the Aurora or JLSC account, so you can also run the code and then use this workshop on your system as well. But for convenience, we also will show it on the Intel Developer Cloud so that you can access the training and then run the code. So with that, I will get started with a few slides and then we will jump into the actual hands-on. So today's topic is mainly part of the Intel GPU optimization guide, and we will mainly be focused on learning what GPU occupancy is and then how to map the workgroups to the hardware. Right, so in the agenda, mainly we will first look at the Intel Data Center GPU Max series architecture, just a high-level architecture of how the GPU looks like. And then we will also learn about how to access these Intel GPUs using the Intel Developer Cloud. And once we get on the Developer Cloud, so we will look at our topic for today, which is mainly look at how we map SYCL workgroups to Intel GPU, and we will learn how to use the Intel GPU Occupancy Calculator and how to calculate the utilization of all the resources on the GPU so that you get the best performance. So we will also look at how to profile the kernels using the SYCL feature. So this will become very important for this series because for almost every kernel, we will be profiling and then getting the performance numbers. So we will learn about that. So which will help us in the next installment of this topic. So the main learning objectives of this course is you will be able to access the Intel Data Center Max GPUs using the Intel Developer Cloud. You will be able to explain how SYCL workgroups map to the Intel GPU hardware. You will be able to use the GPU occupancy calculator to choose the workgroup and subgroup sizes to maximize the GPU occupancy. And then finally, you will be able to enable profiling for kernel execution. So these are the main learning objectives. So with that, so let's get started. So if you have any questions, please post on the chat window. Praveen will be answering the questions or he will interrupt me to answer those questions. Okay, so Intel launched this new GPU called the GPU Data Center Max series. So it's mainly the Intel's highest performing, highest density general purpose discrete GPU, which mainly packs over 1 billion transistor into one package. So the main building block of this GPU is mainly called the Xe core. In the previous generation of Intel GPUs or Intel graphics, we used to refer to this as subslice, as you might remember. So now it has a new name. We call it the XE core. So mainly each XE core will have 8 vector engines, or we used to call that execution units. So this is where all your math operations actually work. So there are 8 vector engines, and there are also 8 matrix engines, or XMX as we call it here. And this block also has a shared local memory, which is shared by all of these vector engines, right? So this make up the building block of the GPU, and many of those XE cores, you can see each one of these XE cores are inside here. So in this case, I think there are 64 of these XE cores, and then there will be 64 ray tracing units, and then with 4 hardware contacts, and this will make up a fully functional GPU, right? So, and this is what we call as a stack, XE stack, and the actual GPU can either have one stack or it can have multiple stacks. But for this series, there is 2 versions available, one with a single stack, and then there's also a version available with 2 stacks, right? So in summary, if we look at the high-level architecture, the compute building block of the XE-HPC-based GPU is a XE core consisting of 8 vector engines, and then 16 XE cores with hardware context will make up a XE slice, and then 4 XE slices will make up a XE stack, which will give you the full GPU functionality. So there might be 1 or more XE stacks present in a GPU, right? So what's available today? So there are 2 data center max GPUs available today. One is the 1100, which has a 56 XE cores, and then there's also 1550, which has 128 XE cores, and this mainly has 1100 is one XE stack, and then the 1550 is 2 XE stacks. So there is a link to a website here. So this will give you more details about each one of these GPU, the hardware specs. So these slides will be sent out after the presentation. Right, so with that, we will straight away jump into the Intel Developer Cloud, and then we will look at the material on the cloud, and then start executing code, right? So to do that, so all you have to do is like sign up for a free account. So most of you, if you have used one of the Intel older dev clouds, you might already have an Intel account. So all you have to do is go to cloud.intel.com and then sign in. Sign into the developer cloud, and then we can proceed with that. So let me share my browser window here. So I think there's a question, which version of GPU is on Aurora? So I think Aurora has the 1550 GPUs. All right, so this is my browser window here. So hopefully you're able to see the screen. So mainly if you go to cloud.intel.com, so you will arrive at this page. So if you already have an account, so just go ahead and then click on sign in. If not, click on get started. So you just have to fill in information like first name, last name, email, and then what kind of work you're doing. And then once you confirm the email, you should be able to log in, right? So once you log in, so you will arrive at the screen, mainly the developer cloud console screens, so which should look like this, what you see here. So this will give you access to all the different hardware. So so this is like you'll get access to a bunch of different hardware, so you can select whichever GPU or CPU you want, and then you can select, and then you can reserve an instance and then to use it, right? So each of these have a different paid model. So this is mainly, if you're doing actual performance work, you can reserve one of these systems to test it on the Intel hardware. But for today's session, you don't have to pay anything. There is a free cluster that's mainly meant for training, and that's what we will be using. So on the main console screen, so there is a tab here called Training and Workshops. So if you can click on that, you will arrive at a page with which shows a bunch of trainings here, which you can launch directly, or you can, on the top right corner, there's a button called Launch Jupyter. So this is what we will be doing today. So go ahead and then click on this button right here, which says Launch Jupyter Lab. Right, so if you click on that, right, so, okay. So if you click on that, you should arrive at the screen that looks like this, right? So it should launch a Jupyter Lab session. Let me know if you're having any issues launching it. If you're launching it for the first time, it might take a few seconds, but then eventually it should look like this. Hopefully this size is visible now. Right, so yeah, so click on the top right corner here, right, which is Launch Jupyter.
We seem to be timing out, most of us. I'll reload.
Okay. Okay, I'll give it a few seconds so that everybody can get started with Jupyter here. Okay, if anybody is able to launch Jupyter, please respond in the chat window so we know at least a few people are able to launch. Okay, so it looks like for some people it's working. For people, if it's taking some time, yeah, please wait. I think there might be a lot of people using the DevCloud at the same time, so it should launch if you refresh and wait. Right, so if you're able to launch, so go ahead and then on this main launcher window, so there will be an option to open the terminal, right? So you can go ahead and then click on that terminal, and I think you will, by default, will be in the root directory. So on the left-hand side, you will notice that there are some pre-populated folders here for training, some big data, and then so on, right? So what we will do today is we will actually clone a repository and then where we have the training, latest training. So let me find that repository. So if you, I will paste this link in the chat window. So if you just Google one API samples GitHub. So this should give you a link to a GitHub repository where we have all the one API and SYCL samples. So we will copy the Git location, and I will go back to my Jupyter terminal, and then in my home directory, I'll just do a git clone and then paste this URL, and this should clone the repository. So I will paste this git clone command in the chat window. So go ahead and then run the git clone in your terminal window. So for people who are using JLSC, they can also do the same thing, right? If you don't want to use the Intel Developer Cloud, so you can also get this training on your cluster and then run the code from there as well. You don't really need Jupyter. You can also run the code just using command line. So if you're using SSH, that's fine too. We just use Jupyter so that it's more interactive, right? So this should take less than a minute to get the entire repository. So hopefully people are able to pull down this repo. So I'll give it a few seconds here. So I think mine is almost complete. So yeah, so it looks like it downloaded on my computer on my cloud here. And once it's done, on the left-hand column, you should see a new folder being created, right? So that's the repository that was downloaded. It's called One API Samples. So if you download it in your home directory, right, using the terminal, so you should have a folder here called One API Samples. Right, so let me know if you're having any issues. If not, the next step is we have to change it to a different branch where we have the latest updates. So that's what we will do next. So go ahead and then do go into that directory. I'll cd into One API Samples, and then I will do git check out development. Okay, so I'll paste the commands that I did. So after I did my git checkout development, so I did
already put in the git checkout development direction. So yeah.
Okay, yeah. First, get into the directory cd One API Samples, and then do git checkout development, and then you should have all the latest updates, right? So. Or I also have this instruction on this page here. So let me put this up. So the entire setup, what we did so far is this so far, right? So we first signed into Intel Developer Cloud, right? So we did that, and then we got into the console. In the console, we went to training and workshops, and then in training and workshops, we clicked on this button that said Launch Jupyter Lab. And once it was launched, we opened a new terminal, we cloned the repository, and then we go into this folder, One API Samples, and then we did git checkout development, right? So this is the full instruction of setup of your dev cloud. So I will paste this link in the chat window as well. So for people who are behind a little bit, so they can use this link to get the developer cloud set up, right? So if you're done with that, so let me go back to my window here. So after this, I mean, you don't need the terminal window anymore. So you have your One API Samples directory here. So go ahead and then click on it. So we will be going into a few directories here. So it's a One API Samples, and then direct programming, and then click on C++ SYCL. Praveen, if you can type the directory path, that'll be good in the chat window. And then we will click on Jupyter, right? So if you click on Jupyter, so we have about 4 training modules here, and today's session we will mainly be focused on GPU optimization SYCL training. So that's the folder we will be going into. So you should all be at this folder here where you have a few training modules, right? So right, so in your Jupyter, it should you should go into direct programming. I will try to paste this in the chat window here. Okay, so I just pasted the directory path. So go into one API, samples, direct programming, C++ SYCL, Jupyter, and then GPU optimization SYCL training. Right, so this will be the. So hopefully people are able to get into that directory, and you should see a bunch of different modules. So in today's session, we will look at the introduction module and also the second module, which is our main topic, which is thread mapping and occupancy, right? So this entire series is also available on the Intel website. So if you just search for Intel GPU optimization guide, you will notice that you'll get 2 links here. So one is the website, one is actually a PDF document for the entire guide. So whatever training you're looking at, you can actually directly access it. You can access the latest training, which will give you all the different modules that you're looking at in the training as well, right? So you can directly access that, or we have also created these modules in Jupyter Notebook to make it easy for training. Okay, so hopefully people are at this point here. So we will go into the first module here, which is Introduction to GPU Optimization. And then inside of that, you will notice that there is a notebook called Introduction. So this is the document we will be looking at. So this document mainly has just an overview of introduction to GPU optimization, how we will be approaching on GPU optimization. So this is just for your information, just reading material if you want to learn about how optimization is done or the approach we are taking, right? So introduction, and then we have a section here which is phases in the optimization workflow. Again, this is just reading material. So there are mainly 4 sections. So the important things you have to keep a note of is the first thing we will do is we will try to keep all the compute resources busy, right? So you have your SYCL code that runs on the GPU. Our main objective is to make sure that we are using all the compute resources, right? So, and this is the topic we will be looking in depth into today. And then the second optimization step is mainly to minimize synchronization between host and device. So this is a topic we will be looking at 4 weeks from now in the second installment of this series. Then the other important step is minimizing the data transfer between host and device. Again, this is something we'll be looking at 4 weeks from now. And then finally, we have another one, right? So when it comes to kernel programming, we have to keep the data in faster memory and use appropriate access patterns, right? So this is mainly optimizing the code by using faster memory, which is shared local memory, instead of accessing continuously from global memory. We look at how to optimize the code to use memory that's closer to the hardware, like either shared local memory or loading it into subgroups and so on. So this is all in the later chapters. So in today's session, mainly we'll look at how to keep all the compute resources busy. right? One thing we will be doing with all the code samples in this series is that we will be profiling and the code so that we can tune the code, right? So for that, we will be using Intel vTune Profiler. So this mainly gives you an overview about how to use Intel vTune Profiler. So what we will do is we will compile the code, and once the code is compiled, we will use the vTune command line to collect the profiling data. And then we will use vTune to actually open the results and then profile the code, right? So the reason we are using command line here is because we are doing this on the cloud, and usually we don't have access to the GUI in the cloud. So you might only have command line access. So this will mainly show you how to use command line to collect all the information. And then we will you can actually install the entire full version of vTune on your local computer, and then just open the collected data on your local computer to analyze the vTune profile results, right? So the detailed steps are here, how to use the command line. So we will be using this. It mainly shows how to run the command line to capture the vTune results, and then we can zip it up, download it from the cloud to your local computer, unzip it, and then open it in the vTune profiler, and then you will be able to analyze it on your local computer. So I will be showing this process in today's workshop as well, right? And so there's also more information in this introduction chapter, mainly stressing on why locality matters, right? So how to keep all the memory that you need for computation closer to the compute engines, right? So it mainly focuses on a lot of memory synchronization and how to minimize memory transfer between host and device. So this is something we will be looking at in the next series of this. But in today's workshop, maybe we'll be looking at how to right size your work, right? So how to choose the size of work groups, for example, or subgroups, so that you maximize the usage of GPU. So this is what we will be focusing on today. And there's other information about different ways to achieve parallelism, right? So we will mainly focus on SYCL programming, but there's also other ways you can parallelize by using compilers like OpenMP. You can also use some parallel libraries like MKL, 1TBB, or 1BPL. And we also have some general description about how the GPU execution model works, and an overview, right? So these are just reading material, a good introduction that you can refer to, right? But to get started in today's workshop, so there is one Hello World sample. So just to make sure that everybody is able to run code on the cloud, we will run this example. So if you look at if you're in this folder, if you just go ahead and then open a new terminal. So what you can do is click on File, New, and then Terminal. And this should open up a terminal, and then I think you should already, no, okay. So we have to go into this directory wherever we have this file. So let me try this one. If you go and then click on the terminal here, yeah, so do this step, click on this plus here, which should open up the launcher. And then if you open the terminal from this interface here, you should already be in the directory that you are, right? So you should already be in this directory. And if you do an ls, you should see this run script called run_hello.sh. So that is the script we will be running. So just do a /run_hello.sh, right? And if you run that, this will just compile and then run a basic hello world application, and you should see the results, right? So let me know if people are able to see this result. The code for this is actually in the lab folder here. So it's a basic hello world where we set up a queue. We have an array of 16 elements, which we initialize from 0 to 15. And then in the kernel code, all we are doing is multiplying each element by 5, and then we print out the result. So the result, you should see multiples of 5, and that it should also display that it's actually running on the GPU, right? So if you're able to run this on your system, that means you're good to go. Your dev cloud is all set up and then running well, right? So if you're actually using JLSC or any other system with GPU, so you can also run it there. Just go ahead and then run this script on your terminal, and then you should see the same result, right? Okay, so let me know if you have any questions. If not, I will jump into the actual topic for today, right? So I was in the introduction folder here on the left-hand side. So I will go back to the main GPU optimization training folder, and I will go into this module 2, which is thread mapping and occupancy, right? So this is our main topic for today. So I will close the other terminals. Okay. So I'll get started with this module here, which is mainly thread mapping on GPU occupancy. And here, just an introduction about how thread mapping actually works. So if you scroll down, you will see that a basic hierarchy of how workload gets executed. So usually if you have a workload with the global size here, these are grouped into smaller groups, which we call as work groups. And each of these work groups are scheduled to execute on the compute units on the hardware, right? So multiple of these work groups can actually execute at the same time, depending on the number of hardware resources available. So that's how we achieve parallelism, right? And each of these work group can be further divided into a smaller group, which we call as subgroup. And subgroup is where it's where a bunch of work items can actually run together in lockstep, right? So those are grouped as subgroups so that we have additional scheduling guarantees, and then we can optimize the code by having that knowing that all the work groups can actually execute at the exact same time, so we can do operations like shuffle or reduction, which will give you much efficient results, right? And the size of the subgroup and the size of the work group will actually have limits, and then it depends on the type of hardware you have, right? So which we will look at. We will compare different GPUs, and then we will look at what are the limits of work group size and then the subgroup size that you can actually choose. So in the next section, we will look at how mapping work groups to XE cores work. So we have a table here. Okay, so I think there is a question here. Praveen, can you answer that? So I think somebody's asking, where is the directory for hello.sh, which is in module 01. If you go to GPU optimization SYCL training, and then if you go into module 01, there should be a hello.sh.
Yeah, I put in the chat window, the complete directory.
Okay, thank you. Okay, so back to this document here. So under this section here, mapping workgroups to XE cores, you will see that there is a table, right? And in this table, we have different generations of GPUs, starting with Gen 9, Gen 11, Gen 12, and then we have the two PVCs, 1100 and 1550, right? So you will notice that so each of these GPUs have different configurations. You'll see that the total number of XE cores, right? So we just looked at the PVCs have 56 and 128, but if you look at the earlier generations, there were 3 XE cores, 8 XE cores, 6 XE cores, and so on. And each one of these XE cores have different number of vector engines, right? So usually it's like 8 vector engines per XE core, but in one of the generation there was like 16 XE vector engines. And then the number of thread also varies, right? So based on this configuration, so we will end up getting, if we calculate the total number of threads, we get different values for different GPUs. And this total number of threads will determine how many operations can actually run in parallel. And depending on each one of these hardware, there's also a limit of a software, mainly software or driver limitation on what is the maximum size of work group. You can see in the earlier generations, it used to be 256, and Gen 12, it used to be 512. And in PVC, the max work group size is actually 1024. So again, we have the building block just showing the same thing that we saw in the slides. So we have the XE core in case of the Max series GPU that we will be using today. So there are 8 vector engines in each one of these XE cores, and then they can be up to 128 XE cores, which make up GPU. So to get started, so let's understand how do we calculate the total number of threads, right? So let's look at a simple kernel function. So in this case, we will use a kernel submission which has a global size of some random value that we picked here, right? It's a 3-dimensional a global size, which is shown here. And then we run this kernel function, and then we will try to compute the occupancy based on different work group size or different subgroup size, and then see how it will actually affect the overall occupancy of the GPU. So the two most important GPU resources are thread contexts. So mainly the kernel should have a sufficient number of threads to utilize the GPU's thread context. And the second one is the SIMD units and the SIMD registers. So the kernel should be organized to vectorize the work items and utilize the SIMD registers, right? So
Actually,
yep.
Can you clarify what the GPU threads are, like the execution units?
Yeah, so it's coming up right here. So we have a simple math here, right? So mainly, okay, so if you want to know what actual threads are, so we have these vector engines. So this vector engines is where you actually submit each one of your work group will execute, and each of these vector engine has 8 threads. So imagine this as an actual compute building block here, which has 8 threads, and 8 parallel execution can actually happen. But there are also 8 vector engines inside this compute block, and then there can be up to 128 of these XE cores. So if you do the math here, so there are 128 XE cores, and then each one of them have 8 vector engines, which will give you 1024. And then each one of those vector engines have 8 threads. So that's how you end up with 8,192 threads that are possible, right? So those are the number of operations that can actually execute in parallel if we utilize the entire GPU. So how do we control the number of threads per work group execution? So mainly, we cannot actually directly set the number of threads, but what we can change is the work group size and then also the subgroup size. So if you want to calculate the number of threads that is being utilized, so you have to just do work group size divided by subgroup size will actually give you the threads, right, for execution. And so we will do a few cases, right, depending on using different work group sizes, and then we will see what is the occupancy. We will be manually doing it, and then we will also eventually learn how to use a tool to actually calculate this occupancy. Okay. So as we know, like there are some parameters like the workgroup size, the subgroup size is something that can be controlled in your program, in your kernel program, right? So everything else is fixed. So each hardware might have a different limit on workgroup size and then also the subgroup size. And the other factor that actually that impacts the calculation is actually the local memory size. So all these three parameters that you see will be different for different GPU that you might pick, right? So it's important to know the limits. So you can actually query for these limits using the SYCL program, and that is the code we have next listed here, right? So if you look at this code here, we have a code example which will mainly print out which will use the SYCL info for the device, and it will find out what the device name is. It will find out what is the maximum workgroup size. It will find out all the different subgroup sizes that are supported, and it will also find out what is the total shared local memory size that's available, and it will just print out, right? So this is a good sample to actually refer if you want to find out what is the limits, or you can also use this in your program. So to run this program within Jupyter Notebook here, so go ahead and then click on this code cell, hit the play button, which will just save the file, right? And then there is a section called build and run. So if you go there, click on that cell, and then if you hit the play button, you should see a star here, and then which means that is actually executing, and then eventually it should print out the result, right? So hopefully you're able to see this result. You can see that there is it tells you that the device name is Data Center Max 1100. The maximum workgroup size is 1024. And then the supported subgroup sizes are 16 and 32. And then the local memory size is 128 kilobytes, right? So if you run this program on different GPUs, you might get different results, right? So for example, I think if you run this on a Gen 9 GPU, so you might get the maximum workgroup sizes 256, and then supported subgroup sizes are usually 8, 16, and 32. And then I think the local memory size is also less in the older generations, which is 64, right? So it is good to know these limits so that when you write your kernel code, you can actually use this maximum number to start off with and then start tuning your code, right? So it's a good program. Okay. So hopefully people are able to get these results. So I've just executed the code right on the Jupyter Notebook. If you want, you can actually open the terminal, or if you're using SSH to your cluster, then you can just go to this directory, right? Go into this 02 directory and then manually run it, run the run_GPU support.sh, right? So I can show you that. So I can go back to the 02 folder, right? Once you're here, I can just do a run GPU support.sh, and then you should get the same results on command line as well. And this is how it will look if you're using SSH connection as well, right? So it should print out all the limits. So hopefully people are able to see this result. Okay. Right. So with that, let's look at an example, right? So let's look at the impact of work item synchronization within a work group. To understand the occupancy calculation, so let's use this as an example. Let's say we are trying to compute the occupancy for Intel data center max GPU, and the total number of work items, which is the global size. We've just chosen this three-dimensional space here, 112, 120, 128. And then we will use workgroup size. We will try to calculate the occupancy using different workgroup sizes, right? We will fix the subgroup size 32 in this case, and then we will change the workgroup size, mainly this R, we will vary, and then we will understand how occupancy actually changes based on different workgroup sizes, right? So if you, so how do we calculate the number of threads? We learned it earlier. Threads is mainly workgroup size divided by subgroup size, right? To start off with, we will use the workgroup size of 128, and then so the total number of threads will be 128 divided by 32, right? So which is workgroup size by subgroup size, and we get the total number of threads as 4. And then each XE core actually has 64 threads, right? Because if you look at this picture up top here, so this is our XE core. So there is 8 vector engines, and there are 8 threads for each one of these vector engines. So there are 64 threads available. So, but if we use 128 as the workgroup size, the total number of threads is 4. So 4 divided by 64 will give you 6.25%, right? So if you only have one work group, so you're only using 6%, 6.25% of the XE core. So how do we make that 100%? So if we actually end up running 16 work groups on each one of the XE cores, then you will end up with 100% occupancy, right?
Hey, Rakshit,
yeah.
Sorry to interrupt. Yeah, one question is, there was a question on the subgroups are similar to CUDA WAPs, right?
Yeah, that's right.
And the question is, are as we are changing programmatically in the subgroup size 16 and 32, it looks like, can you do the same in CUDA WAPs? Is it not supported in CUDA? That's the question.
Okay. Yeah. So in CUDA, there is only a fixed size. So the warp size is always 32. But whereas in case of Intel GPUs, it supports multiple sizes. So you can change the value. So you can manually set it, or you can just let the compiler choose, right? So the best size. So usually if you just let the compiler pick, it will usually pick 32 in most cases. But if you want to change it to 32, change it to 16, you can also do that programmatically, right?
Okay.
But yeah, so I think that's the question, right? Yeah.
Yeah, and another question is it possible to run different work groups in the same vector engine at the same time, right?
Yeah. Yeah, it is possible, right? So they can have so like you can see here, to get 100% occupancy, we have to run 16 work groups can be executed, right? If you run 16 work groups within XE core, then you will get 100% occupancy. So you know that there are 64 threads, right? So up to 64 work groups is possible to run within an XE core, right? So similarly, you can start calculating for different values of workgroup size, right? So in the second case, if you change the workgroup size to 1, 2, 128, which is mainly 256, so which will give you 8 threads, and then you will end up with 12.5%, which means that if you run 8 workgroups within that XE course, you will end up getting 100% occupancy, right? So let's look at the third case, right? So if you choose the workgroup size as 384, so 384 by 32 is 12, and 12 divided by 16 will give you 18.75%, right? So, but if you have 18.5%, then the closest we can reach is 93% occupancy with 5 work groups, right? We cannot run partial work groups in XC Core. So in this case, this may not be a good value to choose, right? So if you choose 384, you know that the maximum occupancy per XC Core is 93%, and then even if you fill up the entire GPU, you will be limited. You will only get 93%. So it may not be a good number to choose. So similarly, you can keep on calculating, right? For different sizes, but there is a limit you will be reaching, right? 1024 is the limit. So if you choose anything more than 1024, you will get an exception, and then you won't be able to compile. But you can see that as and when you increase, we get different XC Core utilization. It's in some cases you get 100%. In some cases it's less than 100%, right? So if you look at the maximum value, 1024, for example, so 1024 by 32 is 32, and then 32 by 64 will give you the occupancy of 50%. So you can have at least, if you run 2 work groups, then you will get 100% occupancy. So you will see that there are multiple cases where you will get 100% occupancy. So then what do you think is the right work group size, right? So obviously we know that launching, mainly dispatching less number of work groups might be beneficial, because submitting each work group has a little bit of overhead. So it's always best to take the highest value and the least number of work groups. So this might be a good number to pick, right? If you choose the work group size as 1024, then you'll get 100% occupancy with 2 work groups, right? So, and it's always good to check the other values too, right? In some cases, maybe computing a smaller work group size might actually end up benefiting and giving you better results. But mainly the goal is here is to understand how to calculate occupancy, and then how to choose the right work group size. So another, there's also impact of how much local memory you can actually use, right? So far we only looked at considering only work group size and then subgroup size. But if you go and look up the picture for the XC Core, you will notice that so you can run up to 64 work groups here, right, inside this XC Core. And then there is only one shared local memory. So this shared local memory of 128 kilobytes is available for this XC Core, right? So let's say, for example, you've written a kernel that that uses 64 kilobytes of memory, right, of shared local memory. So if you use 64, there's only another 64 left, which means that you can only run 2 work groups at the same time, because you're using 64. So that might, use the amount of shared local memory you're using might also limit your occupancy, right? So let's say you can achieve 100% occupancy by using 4 work groups, right? If you need to run 4 work groups here to achieve 100% occupancy, but then if each one of your work group is using 64 kilobytes of shared local memory, then you cannot run 4 work groups. You can only run 2 work groups. So then your occupancy will be 50%, right? So it also becomes very important for you to choose the right shared local memory size, so that you can run enough work groups at the same time in an XC Core. So that's another. So that's why we looked at how to compute how to get the maximum supported shared local memory size, because let's say you want to pick this first case, right? We'll get 100% occupancy as long as you can run 16 work groups, right? Which means that each work group should actually use 128 divided by 16. That's the limit of local memory that can be used. If your kernel uses more local memory, then you might have to go to a different configuration here, right? So in this case, if you're using 64 kilobytes of memory, then this might be a good configuration because you can achieve 100% with only 2 work groups, and 2 work groups can actually use 64 kilobytes of memory, right? Whereas this won't be a good example because if you do this, 4 work groups has to be run, but if you use 64 kilobytes, then only 2 work groups can run here, right? So those 3 parameters become very important on how your kernel is being written, right? So there is also a tool, interactive tool that's available, which you can use to do all this computation, right? So it is good to learn how to manually compute the occupancy, but there's also a tool that is available. So this is it's in GitHub, and it's a web tool that we have written, which will let you calculate occupancy. So all you have to do is like go ahead and then select the type of GPU you want to calculate. So we are using the data center max GPU, and then there's different EU count, right? So the 1100 is actually 448. So that's the default setting. So here you can actually enter the global size of application, and then you can also set the workgroup size and then compute the occupancy, right? So we can do the same thing that we did. So let's say we have 128 and 128 as the workgroup size, and then we have only one workgroup, which is 128, right? So if you calculate the occupancy, you'll get 6.5%, right? Which was same as, let me make this window. So if we looked at our manual calculation here, so if we had the workgroup size as 128, and then if we had only one workgroup, we know that it's 6.25%, right? So you can also, but what if you had 16 work groups available, right? So if you recalculate that, you'll get 100% occupancy, right? So pretty much like what we did here, right? So if you have 16 work groups of size 128, you get 100% occupancy, and that's what you're looking at. But whereas the total GPU occupancy is actually still less, right? Because with only 16 times 128, it's a lot less, because you can have up to 8,192 was the total number of threads for the GPU, right? So we can actually calculate other numbers as well, right? So if you choose the let's say you have 1024, and then you set the one work group of size work group size of 1024, you will notice that you will get 50%, right? Which is same as what we got here. If you choose 1024 as the workgroup size, then 1024 by 32 divided by 64, you get 50% occupancy. But then if you run 2 workgroups, you will get 100% occupancy. So this tool is helpful if you want to compute. So let me refresh and then show you how the tool can be used. So you can vary the workgroup size and then check what are the different options that you can choose to get 100% occupancy. You can also use this slider here, which will show you how much memory you can use and then still get 100% occupancy, right? So in this case, I'm using 0 local memory. So let's say I move the slider to use, let's say 32 kilobytes of local memory, right? But I still get 100% occupancy if I use 32, right? So let's change this to 60, 64. So even now I get 100%, right? But if I start using more than 64, you will notice that my occupancy drops to 50%, right? Because if you were using 80 kilobytes of local memory, that means the second work group cannot run at the same time, because the second work group will need another 80 kilobytes, which is not available because the total limit is 128, right? So this is a good tool to just simulate and see how much occupancy you can get based on different parameters, right? So you can also change the subgroup size and then try to figure out, right? So the important thing to note here is that 100% occupancy does not always mean you will get 100% performance, right? 100% occupancy just means that you're using all the resources in the GPU. In some cases, in some applications, if you're using a lot of global memory access, it's okay to use more memory, right? Your occupancy might actually decrease to 50%, but then the overall performance might actually be better, right? Because using more local memory, you're actually reducing the latency of accessing global memory, so it might end up giving you better performance. So it's this occupancy calculator is a good starting point. It's good to start off with values which will give you 100% occupancy, and then you can start tuning your code to use different sizes of local memory, and then you will have to compute the performance. So it's important to note that occupancy does not always mean you will get the best performance, right? It's a good starting point.
What is SS, DSS occupancy in that calculator?
Oh yeah, so DSS is same as XE core, right? So in the previous version of GPUs, we used to call it the subslice and then dual subslice. That used to be the name for XE core. So this version of occupancy calculator will be updated soon. I think the names will be more clear. I think we've updated to the new names in the later version, which is not released, but SS and DSS is same as XE core. Right. In the previous generation, when we had integrated graphics, we used to call it subslice or dual subslice. And then just in the recent GPU that we have released, that's when the new terminology was introduced. So this will change eventually. This, instead of SS, DSS, it will say XE core.
And could I ask, so there's SS/DSS occupancy, as you said, that's like core occupancy. GPU occupancy, that's like thread occupancy. What's the difference between those two?
Oh yeah, so that is, so we are first calculating the occupancy of this one XE core, right? And then we know that there are 128 of these. So GPU occupancy is just saying that 128 cores for the entire GPU, what is the occupancy, right? So you can do the calculation here. So in this case, so let me put this to 0 here. So we're getting 100% occupancy for the subslice, but then it's still based on the number we have here, right? This is the global size. It is only filling up 66% of the GPU, right? So let's say we have 1024, 56 maybe, 50%. So you know that each work group will give you 50%. So if you have 2 work groups, you will get 100% occupancy for one subslice, and then there are total number of 50. There are 56 XE cores, right? So if your global size is this value, whatever 2 into 10, then you'll get 100% on the GPU as well, right? So you can do that for So it's just so I think you just need to focus on making your XE core occupancy to 100%, and then the GPU will follow that, right? I mean, of course, if you want to fill up 100% of the GPU, you need to have as many 56 times whatever, right? So the actual workload. But if your workload is small, I mean, you can't do anything about it. But at least if we focus on the lowest building block, then that occupancy will follow. Right, and the bottom two tables here will just it just shows you the combination of workgroup, subgroup, and shared memory limits. If you for all these combinations, you will get 100% occupancy, right? It's usually best to pick the highest number, but then it just gives you all the different combination, right? If this could be useful, you can use this. And it also gives you, for the global size that you've chosen, it just gives you all the combinations of valid workgroup sizes that you can actually use, and then the corresponding occupancy that you will be getting. So these two tables are just optional, but then this chart should give you a good idea about how the occupancy changes based on the workgroup size. So you'll notice that 4024, you will get 100% occupancy, and then for 512, you will get it. And also for 600 and something, you'll get almost 100%, right? 680 as the workgroup size. So, so this might be useful to do a quick check while you're designing your kernel code.
Hey, Alexit, one question. So this calculator is using shared local memory and comparing, right? But there's a question on usage of registers like the private memory, and does it show anything on the usage of registers or the private memory for better bandwidth and low latency?
Yeah, I mean, that really is dependent on, using registers versus shared local memory that impacts the performance. But for occupancy, it does not really matter that much. The only thing is, like, whenever you use local memory, it'll probably have a barrier, right? So barrier will also impact. So usually if you choose any local memory, in almost all cases, you will probably use a barrier. So you do have to say yes, that there is a barrier, because I think there are only 32 barrier registers, which will only allow you to run a maximum of 32 work groups. Even though the limit is 64 per XE core, if you are using barrier registers, that limit becomes 32. So that's why there is this limitation as well. But to the question, right? So the private memory, yeah, it affects the performance, but not really the occupancy. Okay. Okay, so with that, let's go to the. So we talked about occupancy calculator, right? And then let's look at an actual example, right? So the same example that I was showing in simulated, I was showing how you can have one work group versus two work group versus three work groups, right? So you can calculate different occupancies. So we have an example here, but this example we have a manual calculation for Gen 9, because this was the previous generation that we used to use, but there's also a new calculation just for the data center max GPU. So this is, we have written a simple vector add example where we are calculating vector add just for one work group, two work group, 8 work group, 16 work group, and then you will notice that if you have one work group, obviously it's like 50%, like we have noted above. If you have two work groups, it'll be 100%, and the XE core occupancy will be 100%. But then depending on how many work groups that are being executed over the GPU, at some point, if we start increasing the total number of work items, then you will achieve 100% at some point, right? And after that, it'll be 100% plus whatever in 100% in one pass, and then the second pass it might be lower, right? So this example mainly is a simple, C equal to A plus B, right? A vector add example, but the only thing we are doing is that we are actually calculating the vector add for with variable count of work groups, right? So we'll start with 1 work group, 2 work group, 3 work group, and then we'll go up to like 1024 work groups. And you can run this code. It will just give you, so mainly hit the play button, which will save, and then hit the play button on build and run, which should compile and then give you the result here in a few seconds. And after it's run, we will try to capture like the VTune profiling information, and then we will analyze the occupancy on VTune, right? So when you hit the play button, you should see a star here, but star means that it's actually running. So it might take some time because the way this free version of DevCloud works is that multiple people can be using the same GPU. So if 2 people are trying to execute this code, it might take more time for your results to come back. So you can see that it's mainly doing vector add multiple times with the total number of work groups changing for every thing, right? So you will notice that for certain number of work groups, because multiple work groups can execute at the same time, the actual performance number doesn't actually change, right? It's the same thing. It's only when you go to a very large number of work groups, that's when you'll see the time doubling because it's using multiple cycles of the GPU, right? So we don't have to worry about the actual performance number here, but what we will do is we will capture the VTune results for this program, right? So when you run this program, you will notice that it will create a binary called a.out by default. So you can see that in the run script here, all we are doing is compiling. This is the command to compile. We set the environment variable, and then we compile it. And then if it is successful, then we run a.out, right? That's what we are doing. And once we have the binary, we can actually run this command here, the VTune command, to actually capture the VTune analysis, right? So what you can do is just copy that entire VTune command, and you can go into the terminal and then make sure you're in the 02 folder, right? And then if you do an ls here, you should see a.out right here. So if you have that file, go ahead and then paste the vtune collect command, which should take like a minute or so to actually run the code, and then it will capture the vtune profiling information, and it will capture all that data into this folder called vtune_data. Right, so this should take a minute or two, depending on how busy the systems are. So mainly what we will be doing is we are capturing the VTune analysis, and then we will see detailed results of what is really happening with the occupancy, right, when we are doing this computation. Right, so it says 75% complete, so it should be complete shortly. So mainly what it's doing is it's just dumping some data into this vtune_data folder, right? So if you've completed your run, you should have a vtune_data folder. And this is what we will analyze, but what we will be doing is downloading this folder to your local computer and then analyzing it on your local computer. But it does require you to install vTune on your local computer, which I'm guessing most of you don't have it. So you can just watch the demo as I do it, right? So if you do have a vTune installed, latest version of vTune installed on your local computer, you can follow along the steps. If not, you can just um, watch the demo. So usually this is the process we do. Once we have the vTune data collected, I will zip up this file and download so that it's easier. So I'll just do tar cbf. I will call this vTune underscore vector add.tgz. And then the vTune underscore data is what we are compressing. So I've compressed this folder. So this compressed folder should arrive here, and you can just download it. So I'll just download it to my local computer here. So you can see that it's downloading. So this might take a few seconds here. Okay, so it's almost complete. So it's downloaded this zip file here. So let me go to my terminal window. Okay, so once it's downloaded, so let me go to the download folder. Okay, so I think the one I downloaded is called vTune underscore vector add. So let me unzip this one here. So I'll just do tar -xvf vTune underscore vector add. So we are mainly downloading it to your local computer because we cannot access the GUI on the dev cloud. We can only have a SSH connection at this point. So what we're doing is we're downloading the data folder, and then we will analyze it with the vTune that's installed locally on your computer. So usually this capture is a pretty large file. It could be up to like 500 megabyte. That's why it takes a while for you to download and then unzip. So once you have it downloaded, it's in my download directory. So I can launch my vTune profiler. So if you install vTune, so this it's free from the Intel One API based toolkit. So you can install it. And once you install it, there is an option to open existing results. So if I can go to my downloads folder, and then I think vTune underscore data is what is my latest copy that I downloaded. So I can open the results here, and then we can see the complete analysis, right? So this usually takes a while, since it's almost 500 gigabytes of data that's collected. Right, so the summary, by default, it'll open up the summary page, but if you go into the graphics tab, then there's a platform tab here, which will give you the analysis of how the occupancy actually varies as you increase the number of work groups that are being submitted, right? So you can see that I have the system that you ran on has 4 GPUs, but we just submitted it to one of the GPUs. So you can see index 0 through 3, and then in my case, it ran on GPU 2 here, I guess, right? And if you look at this graph here, you will see that as and when we increase the number of, so I can zoom in, let me zoom in here. as and when I increase the number of work groups that are submitted, you can see that gradually at some point you will hit 100% occupancy, right? Because if there are enough work groups to fill up the GPU, then it gets you to 100% occupancy. You can see that when it's lower, it's like 17%, and then it goes up to 20%. And then as and when we have more work groups, then you end up reaching 100%. So this is a good tool. So when you run your workload, you can easily just capture, using the same command line, you can capture the profiling data, and you can just put your mouse over your workload, right? So usually you'll have one workload. In my case, we ran multiple workloads with different workgroup size, different number of work groups. So that's why we see a lot of these executions here. So in your case, you might see one, you can just put your mouse over it and then see what is the occupancy you're getting, right? So that's one way to do it. And at the bottom table here, if you open it, expand this one, you will see that you have information for vector add with size 1, 2, 3, 4, and so on, right? With all the sizes that we computed. And if you look at the maximum size at the very bottom here, so as you go higher, you will see that your occupancy actually keeps on increasing, right? The more you fill up your GPU, you'll get better occupancy. And it also gives you other information like the L3 read bandwidth, write bandwidth, number of writes and reads, and all that information. But in this case, we are mainly focused on the occupancy here, right, for every workload. And you can also see the time for execution might be the same, but then as and when there is a larger and larger number of work groups, you'll see that the amount of time it takes for computation is also much longer because it's using multiple GPU cycles to complete all the work group executions. So this is a good way to analyze your application. So you can actually use the same command line to do your analysis, right? So just make sure to change the folder where it's getting saved to describe it in a more meaningful way. And you can just specify your binary name, right? So it will dump everything into a folder. And once you have it in your folder, you can just download it and then analyze it using vTune, right? So again, it just gives you a screenshot of how the analysis looks like. And so this is how you mainly, do your first step of trying to compute the occupancy for your kernel application based on varying your workgroup size, subgroup size, or local memory usage. Right. So let me know if you have any questions on this topic. So, once you have vTune installed on your local machine, you can actually try to download the results and then analyze. And if you have any workloads, you can also, run the same vTune command and then do the analysis on your local computer. So let me know if you have any questions on how to use the GPU occupancy calculator or any other questions on this topic. If nothing else, I'll move on to another one more small topics. I think we have 30 minutes left. So mainly, so we looked at introduction chapter, which is mainly reading material, right? And then the second module is mainly the thread mapping and then occupancy calculator. So that's the second module. The third module we will be doing 4 weeks from now, which is all about memory optimization. So this has optimizing for both USM and then buffers. So we will do that in the next one. So mainly today I also wanted to cover a little bit that's in kernel submission, which is also related to how to calculate the profiling time for kernel submission, right? On the rest of the chapters, so these are all Jupyter notebooks, right? So these are self-learning materials. So it has instruction on what the topic is, and then it has inline code examples which shows how to optimize step by step, right? So you can follow if you're interested in any of these other topics, how to use shared local memory or subgroups, atomics. You can use this as a self-learning tutorial. There's also a topic on explicit, implicit scaling. You're free to go through this material to learn. I think we will have workshops at a later time. Maybe not this year, but next year we will start with the other topics. But you're free to refer to any one of these modules, right? So with that, I will go into chapter 4 here, which is kernel submission. So this is a simple module which mainly talks about how kernel launch actually works, what is the overhead, and then just to understand the basics of what goes on when a kernel gets submitted, right? So it's important for you to know what is the overhead, and then what is the impact of launching a kernel. If you have, what's the impact of launching 2 kernels versus 4 kernels, what is the overhead time. So it's good to understand this topic so that you design your code so that it performs better, right? So mainly, if you look at kernel launch, there is kernel submission start time, which is the time at which the host starts the process of submitting the kernel, right? And the kernel submission end time is the time at which the host finishes submitting the kernel, and then the host performs it performs tasks like queuing, arguments, allocating resources, and so on, which is submission end time is mainly when the host finished submitting the kernel. And then the kernel launch time is the time at which the kernel was submitted by the host and starts executing on the device, right? Because it starts submitting, and then all the queuing and allocating resources will happen, and then the actual kernel will start executing, and that is the launch time. Completion time is when the execution actually finishes, and then you get the result, right? So these are good terminology to remember, so we can actually do the computation of this using just a system clock to understand, right? So to understand that, I have a simple SYCL program here. So kernel, nothing really inside the kernel. You can see that I'm just launching a kernel, but nothing really is inside that. So what I'm doing here is I have a queue, and then I'm starting a clock here, right? Just before I submit the kernel, and then after the kernel is submitted, and this kernel submission using q.parallel4 is asynchronous. So right after that, we have another clock where we are capturing the time, and then we wait for the kernel to complete execution, and then we capture another time, right? So that we can calculate what is the submission time versus what is the submission time plus the execution time, right? So submission time is time that it takes to submit the kernel, which is just the q.parallel4. If you wait for the completion, and that will give you the execution time, which is the second time. So let's run this program. So again, I'll just hit the play button on the cell here, which will mainly give you these times, right? So the submission time is actually 0.06 seconds. The submission plus execution time is 0.064, right? So you can see that with every kernel submission, there will be overhead of 0.06 seconds, right? The execution time here is very small because there's nothing inside the kernel going on, so it's actually 0.002 seconds. So this is important to know, understand that there is a overhead every time you launch a kernel, right? So this is one way to capture the time just by using clocks, but the other way to calculate the time is by actually using the inbuilt driver counters, right? So there is this queue.enable profiling that you can enable while creating the queue. So in the previous case, we just created a queue as just a default queue with no properties. But if you add this property called the enable profiling, then you can actually get the actual execution time of the kernel. Right. So this second example we have here is mainly we've used enable profiling, and then we are doing the same thing, except we are actually calculating the profiling time, right? So you can calculate the profiling time by using this event.get profiling info, and when we get the command start and command end time, and we subtract the two, and which will give you the kernel execution time, right? So if you run this second code example, you will notice that so again, you get the kernel duration is actually 0.064, which 0.06 is almost the submission time, but the actual kernel execution time can be separated out if you use this enable profiling. So now this actually shows that the just the empty kernel that we submitted is actually 0.0015 seconds, right? So if you had an actual kernel, some computation in there, so this kernel execution time is good to have, because it'll only show you the time it took to execute on the GPU, right? So this enable profiling will enable you to capture those timings, right? So so that's one, and we have an example here which is also showing how to execute multiple kernels, right? It'll show you the difference between executing multiple kernels one after the other, which is by using in-order queues, and also like how to execute multiple kernels out of order, right? So it shows you a simple example here, but for every submission, you will see that you can either use it submits three of these kernels by creating different queues. In one of the queue, it adds this property called in-order queue, which will execute multiple queues one after the other. And it creates another queue. By default, it's out of order. And if there's no dependency, then multiple queues, multiple kernels can execute together. So this mainly gives you a way to calculate the kernel submission times when it's in order versus out of order, right? So here you can see that it's just doing a vector add. You can see that if you're doing in order submission, you will see that it's taking 0.35 seconds, whereas if you do out of order execution, multiple queues are executed multiple in parallel, so that's why you see less time, right? So the only difference between the two execution is in order versus out of order, right? So these examples are just basic examples for you to understand how to calculate the execution times, which might become helpful when you're doing performance optimizations, right? Another example that we have here is submitting kernels to multiple queues, right? So if you look at this example here, so mainly what we will be doing is we'll look at the difference when we are submitting to the same queue versus when we are submitting to different queues with the same context, or also submitting to different queues with different contexts, right? So if you look at the code, when we create the code, let's see where we are creating. So we create a default queue with default selector, and then we also create queues Q1, Q2, and Q3. So I think we are creating those queues somewhere here. So we are creating Q0 with in order, and then we are creating Q1 with the same context. We're creating Q1, Q2, and Q3, but all these different queues are created with the same context as Q1 not get context, right? Whereas the last one is Q4, Q5, and Q6. These are all three different queues with three different contexts, right? So if you run this code example, so you will notice that if you analyze the timings here, so first is the out of order, which will give you 0.15 seconds. But if you run these in order, which means each queue is executing one after the other, so that's why this is taking 1.1 seconds. If you have three different queues with the same context, it's taking 0.16 seconds, and then with different contexts, it's 0.1620. So it just gives you the difference in performance based on how you actually select the queues when you're submitting multiple queues, right? So this is again just a simple code example, right? We're not really focused on what the kernel is actually doing, but more focused on how submissions work and how it impacts the performance, right? So these two topics that we've learned is mainly focuses on how to start off with your kernel programming, right? So how to measure the time it takes to launch versus execution time, how to efficiently measure that. So that's one thing. And then the other thing we learned is mainly how to choose your work group size, subgroup size, and then local memory size so that we maximize the occupancy of the GPU, right? So these two, so mainly this optimization guide will, guide you through how to get started. To optimize your code, and then as and when we go through more of these topics, it will deep dive, it will do a deep dive into individual features like shared local memory, subgroups, and so on to optimize your code. So I think this is all the code examples that I wanted to show today. I think we have about less than 20 minutes left. So if there are any questions or if there's any more examples you want me to go over, I can actually do that right now. So let me know if you have any questions.